have experience in programming? No. Anyway, sometimes you have to do like recursive programming to do certain things. Okay, so let me give you an example. A1 equals 3. AN is equal to AN minus 1 plus 4. So the first part of tonight's homework, I'm going to give you a sequence defined recursively, and then I'm going to ask you write the first 5 terms. Well, how do you even begin to do this? Well, what is the first term? Yeah, 3. A1 is the first term, right? A sub 2 is the second, A sub 3 is the third, and so forth. So A1 is 3, so that's the first term. Now, this is called the recursion formula. You have to learn how to read this. What does this mean? If A sub n is any term, what is A sub n minus 1? It's the previous term, right? Because if this is like A sub 4, wouldn't that be A sub 3? It's 1 less. Or if this is A sub 10, then that would be A sub 9, right? So the way to read this is to get any term in the sequence, you take the previous term and add 4. So everything's going to be determined on what the terms that came before it. So if I want the second term, I have to take the first term and add 4, and you get 7. To get the third term, I look at the second term and add 4. If I want the fourth term, you take the third term and add 4. And then if I want the fifth term, you take the fourth term and add 4. There you go. That's the first 5 terms. And then I'm going to ask you, well, what is the 100th term, or the 200th term, or the 1000th term of this sequence? What are you going to do? Keep writing until you get there? No, you use what you learned last night. It's the part I didn't do anything last night. What kind of sequence is this? It's arithmetic. Come on, from last night's homework, you should be able to recognize if it's arithmetic, geometric, or neither. This is arithmetic because you keep on adding 4 every time. So the best way to find the 100th term is to write the explicit formula. So the explicit formula for this sequence is, if the common difference is 4, what do I write? 4n, and then you adjust. If I plug in 1, I want to get 3. So minus 1. So if you want the 100th term, simply plug in 100 and you get 399, right? Okay, so let's look at another one. So we're just going to look at some examples of some recursive sequences. How about A sub 1 equal 5, A sub 2, no, A sub n is equal to A sub n minus 1 times 2. So what are the first 5 terms of this sequence? What are the first 5 terms? Well, the first term is 5. So here's 5. See, if you don't define what the first term is, even though you have the recursion formula, you have no starting place. So to get any term in the sequence, you take the previous term and multiply it by 2. So if you want the second term, you look at the first term and multiply by 2. Third term, and so forth and so forth. So that's easy enough. But now, what if I ask you what is the 100th term? Well, what kind of sequence is this if you keep multiplying by 2? It's geometric. So we have a formula for that. What's the formula for a geometric sequence? A1, the first term, times r to the n minus 1, and what is r? 2. So if you want the 100th term, simply plug in 100, so you're going to get 5 times 2 to the 99. That number is kind of too big to multiply out, but that's how you do it. And then, of course, then you get some little tougher ones like this. What about this? A sub 1 equals 4. A sub n is equal to, okay, let's do a little more challenging one. What about 1/2 A sub n minus 1 plus, no, I changed my mind. What about 2 times A n minus 1 minus n? you write the first 5 terms of this sequence? Well, what's the first term? 4. Now, to get any term in the sequence, you take the previous term, multiply it by 2, and subtract n. But then, what is n? So in this kind of case, what you want to do is plug in numbers. If you want to get the second term, what number would I plug in for n? 2. So plug in 2. A2 is equal to 2A1 minus 2. So to get the second term, multiply the previous term by 2 and then subtract 2. So multiply this by 2, subtract 2. 6. Now to get the third term, what number would I plug in for n? 3. So a sub 3 is equal to 2 times a sub 2 minus 3. So to get the third term, you take the second term, multiply it by 2, and then subtract 3. Take this term, multiply it by 2, 12, subtract 3. None. So you just follow the instructions. If you want the fourth term, plug in 4. A sub 4 is equal to 2 a sub 3 minus 4. So simply plug in 4. It's like a function. Plug in 4 wherever you see n. So to get the fourth term, you have to look at the third term, which is this, multiply it by 2 and subtract 4. 14. And we just need one more. So plug in 5 for n. So 2 times a sub 4 minus 5. So to get the fifth term, you look at the fourth term, multiply by 2, which is 28, and then subtract 5. 23. And there you go. Now this one, I don't think I would ask you what is the 100th term because that's going to be too difficult. Let me see if you could even, yeah, you wouldn't be able to do it. This is too tough for you guys right now. Right now. And of course, the most famous recursive sequence, you guys seen this before. A sub 1 equal 1. A sub 2 equal 1. A sub n is equal to a sub n minus 1 plus a sub n minus 2. Write out the first 10 terms of this sequence. Well, what are the first 2 terms? They're given right here, 1 and 1. 1 and 1. Now, how do you read this recursion formula? To get any term in the sequence, you take the previous term and add the term before that, right? Or if you need to plug in numbers, like if I want to find the third term, I want a sub 3. Plug in 3 for n. A sub 3 equals a sub 2 plus a sub 1. So to get the third term, you add the 2 terms before that, and you get 2. Okay? Now, if you want to plug in numbers, like I said, you can plug in numbers. Plug in 4 for n. A sub 4 equals a sub 3 plus a sub 2. So what is this plus this? 3. But then after a while, you just go, oh, all you're doing is you're adding the previous 2 terms, right? See how recursion depends on the terms that come before it? So what would the next term be? Add the 2 terms before. And then, and then, and then, and then. Okay, how many terms we have? 2, 4, 6, 8, 9. We need one more. Really? 55. There, first 10 terms. And of course, you guys know this as the Fibonacci sequence. Did you see Da Vinci Code, the movie? Or read the book? Yeah, it's all about the Fibonacci sequence there. Now, what if I were to ask you, what is the 100th term of this sequence? Keep on writing till you get to the 100th term. Well, it's not that bad. You probably could do it in, like, if I gave you an hour, you could do it. Okay, but then what if I ask you, because, what is this, 2021? What is the 2021st term? Okay, let me tell you. Because you guys are not, does anybody read books on, like, Fibonacci sequences and things like that? Don't be ridiculous. So the Fibonacci sequence here actually has an explicit formula. This is it. 1 over root 5 times 1 plus root 5 over 2 to the n minus 1 over root 5 times 1 minus root 5 formula for the Fibonacci sequence. So if you plug in 1, you will get this. You plug in 2, you get this. You plug in 3, you get that. So if you want the 100 term, you would plug in 100, but that would be kind of crazy to do, yeah. Maybe it would be faster to just keep writing until you get there. But then, do you notice this number here? Remember? This number came up quite a bit in the first semester. Oh boy, what's going to happen in calculus next year? This is the golden ratio. And what is the golden ratio again? Which is also in the Da Vinci Code. It's the ratio of the length to the width in the most perfect rectangle you can draw. So there's the most perfect rectangle you can draw. We call this the golden rectangle. If you take the ratio of the length to the width, you get the golden ratio, which is approximately 1.618. Does that even sound familiar? And how do you even get this golden rectangle? Well, if you have a rectangle and you make a square over here, right? You have a rectangle, you always can make a square, right? If this leftover rectangle over here is similar to the original one, then that's a golden rectangle. And the golden ratio is simply the ratio of the length to the width in a golden rectangle. Anyway, that's the golden ratio. It shows up all the time in mathematics. Okay, so what are you doing in tonight's homework? Well, I defined some recursive sequences, and then you have to write out the first few terms, find the 100th term. Okay, but then now you get to use your calculator. Okay, I'm going to do a problem very similar to one of those. Okay, so let's say you want to save for your children's college education, because college, the amount that you have to pay for college now is just ridiculous, yeah? So let's say you have a son or daughter, and you want to start saving money for their college education. So you're going to say, you know what, I'm going to put in $10,000 into an account. And how much is the account going to, like what kind of interest rate am I going to get here? Well, in the homework, it says 10% a year, but that's pretty high. And you invested $5,000. Okay, let's do something more realistic. How about 5%? So you put it into an account that earns 5% every year. But on top of that, on the next birthday, you're also going to put in another $5,000. So you put the money in the account, it's going to earn interest, and at the end of the year, you're going to put in another $5,000. And you keep doing that over and over and over until their 18th birthday. How much money is going to be in the account? Well, let's write a recursive formula. What is the first term? 10,000. I'm not going to put the comma. Okay, now let's write the recursion formula. How do I get the next term? How do I figure out how much is in the account on the next birthday? Well, you're putting it into account that's going to earn 5%. So you look at the previous term, which is a sub n minus 1, and if the thing grows by 5%, what do I multiply by? 1.05, right? But then on top of that, you're also going to put in another $5,000. So if the money grows, you put in another $5,000, and you just keep doing this over and over and over. How much money will be in the account at the end on the 18th birthday? So before we actually do it on the calculator, what term do I need to look at to get my answer? How much money will be in the account on their 18th birthday? Do I want the 18th term? 17th term? 19th term? Look, the first term is when they're born. They're 0 years old, right? 1 year later, when they turn 1, that's going to be the second term, right? So what term do I want to look at? The 19th term. You got to remember that because this problem is probably going to be on the quiz. So how do you make sequences on your calculator? Well, let me show you. Maybe we should turn the camera on the screen. You can try that. I wonder if you can see see. I can try to zoom in. Whatever, we'll see if it works. So go to your calculator. You guys have it, at least the app with you. Anyway, the directions are in the thing, right? They always give you directions. So go to apps. If I want to do sequences, which app should I do? Let's scroll. Where's the app? Oh, right here. Gosh, I'm blind. Here's the sequence app. Duh. Okay. So now, you got to know what numbers to punch in. Let's clear everything. Shift, clear. Never mind about clearing. Hey, what's going on here? How come I can't click that? Anyway, so your sequences are, you have, how many different sequences can you do? Hey, this thing is not responding. What happened? I'm gonna close it and reopen it. Something is happening. Shift, clear. Yeah, okay, there you go. Okay, you see up here, you got U1, U2, U3, and if you keep on going down, you got U10. Whoa, U0. Oh, you can do 10 sequences at a time. Yeah, but we'll be happy if we can just do one. Okay, so right here, U sub 1. That's the first term. What should my first term be for this problem? 10,000. So 1, 0, 0, 0, 0. Enter that. Okay, now here is the recursion formula. Now we have to enter. Now instead of using A like I'm using, they're using U1. Okay, so what do I have to do to the previous term? So you're going to go 1.05 times the previous term, which is U. Okay, where's U? Alpha U. And then, you see, you got an n-1 button right here. So you don't really have to punch it in. And then I'm going to add to that 5,000. Enter. Hey, what's the syntax error? What did I do wrong? Okay, let's start all over again. Get rid of that. Okay, 1.05 times. Oh, that's right. It's not U. It's U sub 1. That's why. Sorry about that. So alpha U1 n-1 plus 5,000. Now enter. Okay, there you go. I forgot the 1. And then, of course, you want to start with n equal 1, usually. Okay, now, how can you view a sequence? Well, you can view it in a graph, but the best way to do it, I think, is look at it in a table. So, where can I get a table? Right here, num. Boom! There's your table. And like I said, we want the 19th term, so scroll down. So the 19th term is right there. So on the 18th birthday, you would have $152,122. Enough for 2 years of college, maybe. So if you're going to plan accordingly, you're going to have to put more money in if you want to cover 4 years of college. So that's one way to do it, and that's a good way to do it. But I'm going to show you a faster way. Okay? So go to the home screen. The problem with this method, though, is you're going to have to count on your own. So watch what I'm going to do. Whatever the first term is you punch it in. So 10,000, and then you have to enter it now. Enter. That's the key to this problem. You have to enter that number. Now, you see this button over here on the bottom right? Answer in blue? What does answer give you? You guys even used that button before? Answer is the previous computation that the calculator did. We which is 10,000. So watch what I'm going to do. I'm going to go 1.05 times answer plus $5,000. So what it's going to do, it's going to take the last thing I computed, which is 10,000, multiply it by 1.05, and then it's going to add 5,000 to it. So if you press enter, boom, that's how much there is on your first birthday, or whoever your child's first birthday. And then now you got to count. So first birthday, now when you press enter again, that's what you're going to have on the second birthday. So second birthday, third, fourth, fifth, sixth, seventh, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And there you go. Wait, did I do that correctly? Was that the same answer we had before? Yeah. Why did I say 152,000? I'm looking at the wrong one. We wanted the 19th term. 164,728. Okay, that's more like it. Yes, it's exactly the same. So which way do you like better? Define the sequence, look at it in a table, or just do it in the home screen, but you got to count. Okay, well, you guys can decide, because I don't care which way you do it. You're just going to have to do it. All right, 2 more things we got to learn, and then we're done. Okay, now this game over here. Have you ever seen this game before? Oh, I've got to turn the camera. You can't see anything. Have you seen this game before? Did you play it before? Some people were playing it before. This is called the Tower of Hanoi. Here, let me write that down. Tower of Hanoi. Of course, Hanoi is the capital of Vietnam, yeah? So, this is a game. So on my game, I got 7 discs. They're all different radii. And to play this game, what you try to do is move this pile to a different prong. You only have 3 prongs over here. And there are rules. The rules are you can only move 1 disc at a time, and you cannot have a big disc on a small disc. Okay, you understand? You only can move 1 at a time, and you can't have a bigger one on a smaller one. The objective of this game is to get these discs onto a different prong. So how do you play this game? Well, you start by moving here, and I guess you would move this one here, and then you move that one there. See? And then you just keep doing this until you move it to a different prong. So now you take this one, you have to move it here. Now what do I do with this one right here? Okay, put it in the middle, and then this one can move it over, and then you go here. Hey, I got 3 out of the 7. Okay, now I have no choice. I got to move this one here. Where do I put this one? In the middle or on the right? Okay, move it on the right. Put this in the middle. Put this on the top. And then now this one can move over. And then what do I do with this one? On the left. And then I can put that. Okay, now I got 4 out of the 7 moves. But oh, it's taking more moves every time. And then you just keep on going until you finish, right? But there's a legend that goes with this. So the Buddhist monks in Vietnam, they said that, well, if you had 64 of these discs, and you could move 1 every second, which is pretty hard to do, then what? But when you finish the game, that would be the end of the world. So that's kind of like a really good math puzzle. If you had 64 of these discs, and you could move 1 every second, how long would that take you? How would you solve that problem? Every year I have people saying, well, I would just build it and then I'll just time myself. No, it's going to take a really long time. But your teachers teach you from your early days? If you have a problem that involves large numbers, look for a pattern. Look for a pattern, okay? That's what we're doing in this chapter, sequences, right? We're just defining sequences by looking at its patterns. And of course, when you look at patterns, you want to look at the easiest possible one first, which is one disk. Okay, so let's make a chart. If you have one disk, how many moves will it take to move to a different problem? One. See? One. That's easy. But you gotta start somewhere. Okay, what if you had two disks? How many moves is it gonna take? Can you visually do it? One, two, three. Oh! So two disks takes 3 moves. Do you see the pattern? What, it's gonna be odd numbers? The next one's gonna be 5. What's your guess? Well, let's see. How many moves is it gonna take to do this? 1, 2, 3, 4, 5, 6, 7. Oh, 3 moves take 7. 3 disks take 7 moves. Are you guys trying to figure out the pattern? What's the next one gonna be?
13.
What's the pattern? Add 2, add 4. So the next one, add 6, 13. Well, let's see. How many moves is it gonna take? 1, 2, 3, 4, 5, 6, 7, 8. Where do I put this one? This one? No, here? Here? Okay, what's the count?
9.
No. 8, right?
9.
This one's 9.
Are you sure?
Yes.
9, 10, 11, 12, 13, 14, 15. You're right, it is 15. Okay, now we got the pattern then.
No.
Okay, we gotta do 5. We don't have the pattern yet. Okay, so here we have 5 disks. Now some of you see the pattern. Some of you are still befuddled. Okay, now let's use some mathematical ingenuity here. Look. I'm not gonna do it because now it's gonna take a long, the more you have on here, the longer it's gonna take. So maybe we can go, well, you see this 4 on the top here? Without actually doing it, how many moves will it take to move these 4 to a different problem over here? 4 disks takes 15 moves, right? So without actually doing it, we can learn right here. 15, so it took me 15 to do this, and then 1, and then without doing it, how many moves is it gonna take to move these 4 on top here? Another 15, so that's 15 plus 1 plus 15. 31.
Oh.
You guys see the pattern yet?
Yes.
Okay, so now I have 6 disks. Without actually doing it, how many moves is it gonna take to move these 5 over here? 31 plus 1 plus 31. So 31 plus 1 plus 30. So it's this plus 1 plus this. Hey, Mr. Park, isn't that just doubling it and then adding 1 then? Yeah, that's the pattern we were looking for. To get any term, you just take the previous term. See how it's recursive? You look at the previous term, you double that, and then you add 1. So you get 53. So what would it be for 7 disks? Double that and add 1.
127.
127. Okay, what about 8? Double that and add 1.
255.
255. And we just keep on doing this till we get to 64 disks, yeah? No, that doesn't take so long. Okay, you guys think you can do it? Okay, we're gonna do it then. 9. 511. Ooh, Tanaka thinks she's good. 10.
1020.
123. Okay, we're almost to 12.
2047.
2047. Okay. 12.
4095.
4,095.
95.
Okay, 13. We just have to get to 64, you know.
8180.
8,000.
8,190.
100.
91.
91, okay, 14. Tell me when you give up. We gotta get to 64, this is crazy.
16,000.
So now that we got the formula, okay, in fact, how do you write this recursive formula? What is the first term?
1.
1. To get any term in the sequence, you take the previous term, multiply it by 2, and add 1. Okay, we got that. But if I want the 64th term, I don't want to just keep doing this, so maybe we need an explicit formula. So look at the numbers in this sequence over here. We got 1, 3, 7, 15, 31, 63. I think we might have seen this yesterday. That's why I said it's going to be important. What is the explicit formula for this sequence? I forget. Somebody over here got it. It was 24 hours ago, people. I'll give you a hint. These numbers are all one smaller than something you know. 2 minus 1, 4 minus 1, 8 minus 1, 16 minus 1, 32 minus 1. And what is 2, 4, 8, 16, 32? Those are the powers of 2. 2 to the 1 minus 1. 2 to the 2 minus 1. 2 to the 3 minus 1. 2 to the 4 minus 1. So what would be the explicit formula?
2 to the n.
2 to the n minus 1. Now do you remember from yesterday? That's why I brought it up yesterday. So if I want the 64th term, I'm not going to do this. I'm just going to use the explicit formula. So the 64th term would be 2 to the 64 minus 1. And if you could move one move every second, that's how many seconds it will take. Now, do you guys have any idea how big that number is? It's pretty big. Okay, you got your calculator out. Compute this number.
1.845 times 10 to the 19.
So if the number is so big, it gives it to you in scientific notation then. 10 to the 19th power. That's a lot of zeros, Mr. Park. Okay, so maybe we should convert it into things we can understand. Let's do some dimensional analysis. How do I convert seconds into hours? So we need seconds on the bottoms and hours on the top. And from physics, you guys know this already, right? 1 hour is 3,600 seconds, right? Okay, do that on the calculator. You already got the number on the screen, just divide it by 3,600.
5.12 times 10 to the 15.
We still got 10 to the 15. That's big. So why don't we convert the hours into days then? So we need hours on the bottom and days on the top. So 1 day is 24 hours. Take that answer you got now, divide it by 24.
2.14 times 10 to the 14.
That's still too big, Mr. Park, okay? So let's convert into years. So days on the bottom, years on the top. What do we know? 1 year is, come on, physics people. Thank you, 365.25. How come? Okay, and it's actually 365.24999, I think, or something like that. Because every 100 years you gotta add 1 more day as well, yeah? I don't know, I wasn't alive then. Okay, anyway, do that, the days cancel out. Okay, this will tell you how many years, and we're not gonna go past years.
500.
Wait, don't tell me. Let's see if I can remember something from last year when I did this. 5.85 times 10 to the 11. Is that what you got? That's what I remember.
Yeah.
Yeah. So what is that? Well, 10 to the 9 is a billion, right? Or we have to go smaller. 10 to the 6 is a million. 10 to the 9 is a billion. So this is 585 billion years. So that means if you have 64 disks and you could move one every second, it would take you 585 billion years. Mr. Park, that's not that long. What is the age of the Earth right now? No, come on.
4 billion.
Isn't it between, is that right? I thought it was between, okay, I'll take your word for it, about 4 billion years old. So 585 billion, that's a long time. So anyway, Anyway, so again, the reason why I tell you guys stuff is because it's gonna come up, and hopefully you can remember. Okay, this will definitely come up on a quiz or a test, even the Fibonacci one. Hopefully you remember something there. Now, one more thing I gotta teach you. It's gonna come up with tonight's homework. So, if you look at this recursion formula over here, so it doesn't matter what the first term is, but anytime you take the previous term, you multiply it by something, and then you add something to it. We call this linear recursion. That's because this formula looks like a linear function, y equal mx plus b. I didn't make this up, okay? I'm just relaying the information to you. Okay, so tonight's homework, let me get rid of that thing. You're gonna have to handle linear recursion. Okay, look at problem 8b. In fact, I put it in parentheses. It says linear recursion. See how it doesn't matter what the first term is, you take, to get any term in the sequence, if you take the previous term, multiply it by whatever number, and then add something to it, that's called linear recursion. So let me show you something about linear recursion, and then we're done. Okay, so let me do a one similar to that. Okay, so let's say the first term is equal to 12. To get any term in the sequence, you take the previous term and let's say multiply it by 2/3 and then add 1. Okay, let's write out the first few terms just to get a feel of it. What's the first term? 12. What's the second term? To get the second term, you got to take the previous term, which is 12, multiply it by 2/3, and then add 1. 9. How do we get the third term? Multiply this by 2/3 and add 1. 7. Okay. Multiply this by 2/3, add 1. Uh-oh. 17. Oh my God, we got fractions, Mr. Park. Okay, multiply this by 2/3 and add 1. Oh no. See what happens when you guys put fractions in there? Look, 17/3 times 2/3 is 34/9, and you add 1. 43/9, and then we won't even bother trying the second one, yeah? So you know what question I'm going to ask you? I mean, the next one? What is the explicit formula for this sequence? Because that's what you're going to have to do. Number 8, write in explicit formula. Well, if I didn't have the plus 1, what kind of sequence would that be when you keep multiplying the previous term by 2/3? That's geometric, right? When you keep multiplying by something. Okay, so if you didn't have the plus 1, that would be geometric, but by adding the 1, what it does, it kind of mutates it. It's like a mutation of a geometric sequence. So, watch what I'm going to do here now. So to get the explicit formula for this sequence, since you keep multiplying by 2/3, it's going to be kind of like a geometric sequence. Anytime you have a number to the nth power, that's geometric, right? Think about it. Plug in 1, 2, 3, 4, 5. It keeps multiplying by 2/3. But it's going to be a mutation of that. So you multiply it by some constant. In other words, kind of stretch or shrink the graph. And then you either shift it up or down. This is the mutation. So you got to remember this. I don't think they teach you this in any books either. Okay, so anytime you see linear recursion, and it's easy to memorize, you see this number there? That's the number that you put here. Okay? Now, how can I figure out what the constants A and B are? Just like when I taught you, remember, what did I teach you yesterday? The method of finite differences. You're going to solve systems of equations. That's what we're going to do here. So if we know this is the formula, if I plug in 1 for n, shouldn't I get the first term? If I plug in 2 for n, shouldn't you get the second term? And since there's only 2 letters to find, we only have to solve 2 equations, 2 variables. So let's see if we can do that. Plug in 1 for n. 2/3 a plus b, that has to equal to the first term. Now plug in 2 for n. You gotta deal with fractions. 2/3 to the second power. 4/9 A plus B, that has to equal to the second term. Thank goodness I don't need those. Yeah, you really only need the first two terms if you recognize it as linear recursion. Now, can you solve these two equations, two variables? Oh boy. Okay, I'll tell you, instead of 2/3, why don't we change that to 6/9? What should I do with these two equations? Add, subtract, multiply, or divide? Subtract. Okay, if you subtract, you get 2/9 A is equal to 3. Therefore, A has to equal 27/2. Now, once you figure out A, plug it back into one of these. Maybe I should change this back to 2/3 now. I don't know which one you want to plug it into. Okay, let's plug it into the second one. 4/9 times 27/2 plus B equal 9. 9 goes into 27 3 times. 2 goes into 4 2 times. So 6 plus B equal 9. B equal 3. Why did I write it twice? I don't know. Therefore, the explicit formula is 27/2 times 2/3 to the n plus 3. That's the explicit formula. And if you don't believe me, try plug in 1. If you plug in 1, do I get this? Look, if you plug in 1, you get 2/3. The 2's cancel out. 3 goes into 27 9 times. 9 plus 3, it's 12. It works, Mr. Park. What about when I plug in 2? You're going to get 27/2 times 4/9 plus 3. To 3, to 2, you get 6 plus 3, 9. It works. Yeah, but is it going to work for the second one, Mr. Park? Well, let's try. 27/2, what is 2/3 cubed? Really? 8, 27 plus 3. 27's cancel out. 4 plus 3, 7. It works. Why would I teach you something that doesn't work? It works. So anytime you have linear recursion, do you guys understand how to recognize linear recursion? When you have a term is equal to the previous term times a number plus another number. And this is what you have to do to get the explicit formula. Why do we need the explicit formula? Well, you're going to find out after we do the next lesson. Okay, any questions on this? Okay, so what the next lesson is, and we're not going to see the next lesson until after the test, you're going to have to know your base graphs. Uh-oh. And remember Lomi Lomi and Huli and massage? Remember that thing? The reason it keeps coming up is because it's going to be in calculus. All right, we're done. You got 6 minutes left. Kusumoto, is there going to be